Lesson 1.5, Descriptive Modeling and Accuracy. Precision and accuracy are not the same concept, but they are often confused with one another because they are very similar. So let's look at the difference between the two. In our unit, they used a bullseye to describe the difference, which is really a good visual, so we're going to use that. Here we have arrows just kind of all over the bullseye. This is not precise and it's not accurate. Here we have arrows all concentrated in one place. This is very precise, but it's not accurate because our accuracy would have occurred here in the middle in the bullseye. That's where we were trying to reach. Here we're accurate because we're very close to the bullseye, to the center, but we're not really precise because we're kind of all over the place. And then here in our last example, we're both precise and accurate. Okay, so precision is more about obtaining the same results over and over again. Accuracy is obtaining desired results. And in math, we generally want to be both precise and accurate, although sometimes accuracy is more important and sometimes precision is more important. When we're rounding, we want to determine the level of accuracy we need in order to see if we're achieving our goals. And we use significant figures to determine that level of accuracy. Now, significant figures are critical when we report scientific data because they give you an idea of how well you can actually measure or report your data. So, you know, especially with scientific weights and things of that nature, you may not be able to record data as accurately as you would like to. Okay, but let's look at the rules for significant figures. First, any number that is not 0 is significant. Zeros between non-zero numbers are significant. These zeros are significant. They are between non-zeros. Zeros which are to the right of a decimal point and at the end of the number are always significant. For an example, I'm at the right of the decimal point and I'm at the end of the number, so that is significant. Zeros which are to the left of a decimal point are significant. So if I write 3600 and I put a decimal point, that makes the zeros significant. If I do not put a decimal point, they are not significant. If we can write the number in scientific notation and we can get rid of the zeros, they're not significant. And we will talk about scientific notation later in the unit, in the course. But for now, following these rules is what you'll need to do. So why is it important? Well, it's important because it lets us know what we need to round to when we're doing some calculations. If we're not told a specific decimal place, then we need to do significant figures. So when we add or subtract, we're going to count the number of decimal places to determine the number of significant figures. We can't have more decimal places than the number with the smallest number of decimal places. So we look at this. If I'm doing this addition problem, I have 6 decimal places, 4 decimal places, and 2 decimal places. When I add this, this is my actual answer. 24.694633. But the answer I want only has 2 decimal places because I only had 2 decimal places in my smallest number of decimal places, so I can only have 2 decimal places in my answer. So this is the answer that I need to give. So when we talk about multiplication, it's a little different. When we multiply our significant figures, our answer cannot contain more significant figures than the numbers being multiplied or divided with the least number of significant figures. So when you add or subtract, it's the smallest number of decimals. When you multiply or divide, you're talking about the actual total number of significant figures. So if we look at an example, we're multiplying. I have 8 significant figures and I have 5 significant figures. So when I multiply this, my actual answer has 1, 2, 3, 4, 5, 6, 7, 8 significant figures. But my least amount was 5 in my problem, so I can only have 5 significant figures. So this is the answer I give. So let's look at some examples. How many significant figures we have? I have 1, 2, 3, and since this is after a decimal, it does count. So I have 4 significant figures. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now these zeros here and here are counting because they're before a decimal point. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. If I had a number like this, I would have 2 significant figures. Okay. Now I'm going to add these together on the calculator, and I'm going to give you my answer, the actual answer, and then I'm going to round it to the right number of significant figures. So when I add 34.66 plus 333, I get 367.66. Now, I had 2 decimal places and I had 1 decimal place, so my answer can only have 1 decimal place. So I have to round it to 367.7. When I add my next one, so 1.23 plus 9.66, I get 10.89. I have 2 decimal places in both, so I keep my 2 decimal places. 445 minus 1.22 gives me 443.78, but I have no decimal places, so I can have no decimal places in my answer, so I need to round that to 444. Why don't you try these 3 and round them to the correct number of significant figures and then check your answers? So just pause for a moment and try them. Okay, so when I added D, I got 20.198, but 18.2 only has 1 decimal place, so my answer could only have 1 decimal place, so I rounded. 10.2 minus 1.34 gave me 8.86. Again, only 1 decimal place, so I had to round. And then 100 minus 23 had no decimal places, so my answer also has no decimal places. Let's try some multiplication. And if I do 12 times 11.45, I get 137.4. Now, I have 2 significant figures and 4 significant figures. I have to round this to 2 significant figures. So I need to round this to 140 because 140 only has 2 significant figures. When I multiply with my scientific notation, I multiply the decimal part, so 1.23 times 6.4, which will give me 7.872, and then I add the exponents, so times 10 to the 5th. Here I have 2 significant figures and 3, so I can only have 2, so I need to round And that will give me 7.9 times 10 to the 5th. 5.233 times 6.324 is 33.093492. I have 4 significant figures, so I have to round to 2 decimal places, giving me 4 significant figures. Dividing works the same way. If I do 34 divided by 22, I actually get this very long decimal. It's a 1.5454, etc. It repeats. But I only had 2 significant figures, so I can only have 2 significant figures in my answer. Dividing with scientific notation, I divide the numerical part. Okay, now if I multiply this by 10 to the 5th, it would multiply out, and I'd move this decimal place 5 spaces. But I only had 2 significant figures, so I can only have 2 significant figures here. So I can write it like that, or I can adjust it and write it like that in order to have the 2 significant figures. Sorry, that wouldn't be 10 to the 5th, that would be 10 to the 4th. Okay. Next, I divide 100.23 divided by 5.22. Three significant figures is my smallest amount, so I have to have 3 significant figures in my answer, so 19.2. Okay, we're going to go ahead and skip this next section and move on to choosing appropriate units. Another aspect of precision and accuracy is to choose the appropriate units. So we wouldn't measure a necklace in miles, we wouldn't measure the distance to the moon in millimeters. So the right choice of unit improves accuracy because it's very difficult to measure accurately if you're using the wrong units. So a good rule of thumb is to choose a unit of measurement that is most likely to give you small whole number results. So measuring a necklace, we wouldn't use miles or yards because we would get some crazy decimals. We could use feet if it was a long necklace, but inches is probably the most appropriate unit. And if measuring the distance to the moon, we're not going to use miles, or I'm sorry, we're not going to use millimeters, we're going to use miles or kilometers, because millimeters, feet, yards, meters would give us very large numbers, and it would be very hard to measure that distance. So let's choose some appropriate units. If I'm measuring the weight of a paper clip, am I going to use grams or kilograms? Well, a kilogram is 1,000 grams. A gram is actually very small, so I'm going to use grams. How far I can throw a ball, yards or miles. For me, it's actually probably inches, but we'll go ahead and go with yards. A tube of toothpaste, ounces or gallons? Well, toothpaste tubes are pretty small. Tree, centimeters or meters? Choose meters. The length of my arm in centimeters or meters? 1 meter is approximately 3 feet, so you might, if you have long arms, be able to measure it in meters, but I would go ahead and suggest centimeters to get the most accurate results. Our rope for playing tug of war, we're going to measure in yards. A loaf of bread, grams or kilograms? Well, we need to know how much a kilogram actually weighs. I mean, I know it's 1,000 grams, but in relation to something that I'm more familiar with, like pounds, a kilogram weighs 2 pounds approximately. Well, a loaf of bread is probably not 2 pounds, so I might use grams. A butter knife would be inches. Water used to wash my clothes in a normal washing machine, it's going to be gallons. And the string needed to fly a kite in meters, unless we don't want to fly very hard. So hopefully That all made sense?